Yeah, hi and welcome to my talk on Service Meshed Enterprise Java with Istio. And I'm very happy to be back in Ukraine. It has been 2 years since I've been here for the first time, and I'm happy to talk about this topic today. So, my name is Sebastian Daschner, born and raised in Munich, Germany. And now for a little bit more than 3 weeks, I work for this company called IBM, and I do a lot of stuff on Java and enterprise in general. And today I'm here to tell you why you should be enthusiastic about service meshes and about that technology. So a quick poll up front: who of you knows about Istio or heard at least the name? Hands up. Okay, most of you. And I guess Kubernetes is also a thing, and Docker. Yeah, okay, most of you. That's good. So I want to show you why we enterprise developers should care about that technology and why that is something that we can use in enterprise projects. And to do so, of course, I think slides are boring, so I want to show you a lot of live coding, or at least as much as possible. And to do that, I have an example for you, a microservice example to, well, show a little bit live what we can do that. And if you know me, then you might know Ja Lublu Coffee. So I have a coffee example for you about enterprise coffee, which is a very basic microservice, quote unquote, example. So at least we have two applications here. Why two? Well, one is kind of boring, and we want to have at least some communication going on in our service mesh, in our mesh of microservice deployments. Otherwise, that would be quite pointless, right? So we have two applications, and how that quickly looks like. I want to show you. If we have one called that is coffee shop, where we as a customer go to order some coffee at the coffee shop, right? And then we have that friendly barista person that then brews the coffee for you, right? Like the ones you find upstairs. So what we do as a customer, as a client, we make a client call at the coffee shop service to say something like an order coffee invocation. We can do that, for example, by HTTP or whatever protocol we define. And then, just for the sake of the example, what we will do here, we will have a synchronous call to this backend, to this barista application. Something like, please start the coffee brewing process. And that will then just return synchronously for us, so just for the sake of the example. So let's do this, and let me quickly introduce the application for you. So what we have is, well, of course, a Maven application. A Maven or Gradle is typically what you would do. And I want to show this using a Java EE approach. So we use the latest Java EE 8 version and built this as an application that later on will be deployed to, well, of course, Docker containers and all that. And just because I'm brave enough, I will build this using JDK 11. Who of you uses Java 11 in production? Hands up. Yeah, that's what I thought. Okay, JDK 10 in production. 9? Okay, everyone, JDK 8? Yeah, that's what I thought. Okay, well, anyway, I use 11, and luckily that works for, well, the application server that I use and everything. And I'm going to show that running on OpenLiberty, and then, of course, Docker, Kubernetes, and this Istio service mesh technology. So what I have here, let me just briefly walk you through this example in the code so you roughly know what's going on. I have a Java EE application that uses JAX-RS, the standards, well, for RESTful web services. So I have something like an orders resource where you go to this resource, the URL something /orders, and then you can get orders or post new orders and so on and so forth. And that's most of it that you should be interested in. So it's not that much about the application itself for now, but just about the basic workflow, how that works. So if we want to order a new coffee, say, dear coffee shop, we want to have a new coffee. So we post a new coffee order in JSON or anything else to that system and saying, please order a new coffee, which makes us use that internal component that basically says, well, not much, barista, that's another component, please start the coffee brewing process. So of course, this now has to be some client functionality, because this will connect then to the second backend, to the application, right? So what that has, well, that has an HTTP client internally, and what we do, we use JAX-RS also on the client side. We can use anything else. It just has to be a HTTP client. So these two connections between the systems will be HTTP calls, and then we call that, right? And that's all for it for now. And the second application, well, that actually looks even simpler. We have another resource. It's called brews, where we just, well, basically say these are the coffee brews, accept them, and then, well, return, basically. So anyway, now we want to run this in our cloud native setting, right? In a Kubernetes cluster and then later on in an Istio cluster. To do that, we will build this as, well, a Docker image, right? We want to have a Docker container running later on, and I'm pretty sure you're familiar with that, how that looks. So we have Docker files here in our application. The Docker files specify basically everything that our application needs in order to run, right? Whatever that is included, independent of the technology. So for our Java Enterprise app, of course, we need our application, right? And then we need some kind of runtime, like an application container, and, well, Java, right? And some optional configuration, and so on and so forth. And for us, that is already included in a base image, where I say, please give me I use OpenLiberty for Java E8 application server, including some configuration, add some server configuration here, and then finally add our application. So that's the so-called thin deployment artifact approach. So let's do this. We're going to build our application. I have my command line here. Let's switch to the coffee shop folder. We use Maven to build that, so we do something like Maven clean package to build our enterprise app that is packaged as a WAR file here, as a thin WAR approach. And then we used, well, Docker build. You are probably familiar with that, right? To say, this should be my coffee shop private repository, and this is called service mesh build number 1, build it, and then, of course, let's hope that the Wi-Fi works properly. We're going to push this to our repository. So a nice thing about that is if, well, let's see how that works. If you use a thin deployment artifact approach, where you basically have a very thin target moving point, oops, that's not good, that you ship, then what you push each and every time, that transfer, that is actually tiny. Because the megabytes of data that you have in your Docker image, the Java installation plus your application server, well, let's see if that works out later. Well, it's actually already prepared. It's already there, so I don't have to push it, but let's see if the network is with us later on. That means you don't have to push this, all these megabytes of data of the Java version that you have and of your application container, basically of your implementation, each and every time, because the WAR file that you built is actually very small. We can go into detail later on. It's like 14K. It does not include any application. And of course, with Docker's copy on write file system approach, that leverages this, and you save a lot of time by building and by transferring your image. But anyway, we can build this for the coffee shop project, and the same is true if we build our second application that looks, well, very similar. It's also Java E application that ships to very similar WAR file and has a very similar Docker file. If we look in that, we basically just change, well, the name of our application, right? So we can Docker build this as well and say this is called Barista. With that specific build number, we're going to build and then push this. I'll try this one more time for that image. Otherwise, let's just pray for the best later on. Well, and then we have a Docker image that we could run locally, right? But that's pretty boring. We've probably done that before. So we don't want to run it locally. We actually want to run it in a cluster. So we want to run it in a Kubernetes environment, right? Something like this. Kubernetes is the de facto container orchestration. So basically a similar approach to what we did for Docker images, basically specifying how our runtime looks like in a declarative approach in these Docker files, can be done for the overall cluster as well, right? We can specify with so-called infrastructure as code files how our environment looks like. So which services we have, what are the load balancers and the network configuration, and so on and so forth, which is very well helpful in terms of how we want to set up our environment. So what we do then is basically how our coffee shop and barista service then looks in a container orchestration is we define so-called services. A service in Kubernetes is very similar to a microservice idea. It's basically a logical abstraction over an application, such as coffee shop or barista. And then we have one or more running instances. They are so-called pods. Pods is, well, basically a running container, or in brackets, one or more running Docker containers that run here for the instances, and that are then backed by this service. So we have a service that is a load balancer, and that will balance the load to our running instances. We have one for the coffee shop and for the barista system. So if we make a call to the coffee shop, then later on, if we invoke that as a client, we basically go to the service that forwards it to our main container, to our running instance. And then if the main container, as we just saw in the code, will make a call to the barista backend as well, well, that also works in the cluster by looking up the service name barista and by just invoking this container. So I guess most of you are familiar how Kubernetes files look like, right? We have this YAML file format. Who of you knows the YAML file format or has used that before? Who of you likes the YAML file format? Oh, one guy. Well, a few, at least. So in these YAML file formats, we have a declarative way how to specify these Kubernetes resources. So first of all, we specify a so-called service that we have, for example, for our coffee shop. That is quite simple. A service has basically a name, and then we define which ports we forward to our application. And then we specify what is our running application. What do we run here actually? So what we want to run is, well, a Docker image first of all. So we tell our application where to find that Docker image, this one, and tell it also, well, how many instances do you want to run? Well, first of all, one, right? One replica. Or we could increase that number if you like. So a deployment is a logical abstraction over pods. It will manage these pods for us. We could also use a pod definition to just create one pod, but we don't. We actually want to manage this over that. So the same is true for the barista definition. That basically defines a service for the barista, same story here, and of course a deployment as well, where we say we want to deploy that image with one replica. And that's already a very nice story, because how do we actually configure the coffee shop system, which backend to use? Which IP address we use, or which DNS? Did we do that? Well, we actually don't really want to configure that, right? Because one approach of the so-called 12-factor application is don't store configuration in the application, don't hard-code it, but provide it from the outside. But it's actually quite annoying to say we have our test environments and our staging environment and our production environment, and in all of these three environments we have to reconfigure how we look up the external system, right? We have to reconfigure the different IP addresses, and they might change also, and that's, well, quite annoying. Actually, if we use Kubernetes, there's good news. What we have here, and this is again my HTTP client in my barista system, in my coffee shop system. If you look at that URL, you see the good news is we don't really specify an IP. We simply write barista as a host name, plus the port 9080. That is the default port for OpenLiberty. Why can we do that? Why can't we just write barista? Well, the good news is Kubernetes does a cluster internal DNS resolution for all the service names. So that is not even a service mesh feature, that's just a Kubernetes feature. And what happens is if you have a service definition, such as this one, with the barista name, then what happens for the barista host name, Kubernetes will resolve the IP addresses of all the pods, of all the instances that back the service in a round-robin approach. So we can simply look up HTTP barista as a host name, and then we will get the correct system. And this works in the test environment and the staging environment and in the production environment, because in all of these clusters and namespaces, they will have the correct resolution of their corresponding service, which is good for us, because then we can actually just hard-code it, that URL, and not care about it much more. So that's it. That's a nice feature of that as well. This is how we do the lookup, and then we basically can deploy this. So let's do this. Okay, that didn't work, but let's pray that the rest of the network, oh yeah, that works luckily. So we have a Kubernetes cluster here with kubectl, kubecontrol. That does not run on my laptop. It actually runs in the cloud, of course. So I use the IBM Cloud Managed Kubernetes because that's easy to set up. And there we go. But now, as you can see, there's just a default service and no pod. It's basically empty. That's an empty cluster. There's nothing running there. So let's change this. Let's say we want to add our resources that we just wrote in this fancy YAML into the cluster that we usually do by kubecontrol create or kubecontrol apply, to say we apply the coffee shop deployment, everything that's in that folder, please apply it. And the same is true for our barista deployment. You just saw the YAML there, and we're going to create that as well. And then luckily we have two more services, one for the coffee shop and one for the barista system. Okay, that's good news. And hopefully we also have the pods, because we specified deployments, that deployments manage the pod. And you remember we have one replica each, so we have one replica, one instance for the coffee shop and the barista system. That's good news, and they also are up and running. That's fine. They're not ready yet, so the application server needs some time to start up. We included probes to tell Kubernetes once that thing is up and running, because actually Kubernetes doesn't really know when they are up and running, because Kubernetes does not know that we run a Java application or whatever we run there, right? It just starts up the Docker container, and that's just a Linux process. That's fine, it just starts it up and it's happy. So we actually have to tell Kubernetes with so-called probes once our application is up and running. So we tell them liveness, that means the application is running at all, when that is the case, and also the readiness probe. That tells Kubernetes once our application is ready to do some meaningful work, ready to serve some traffic. And that is shown here. And oh, that is already up and running, that's good. And the second one will be up and running right now. So hopefully we can now order some coffee. Apparently that application is there now. Let's see. I could use any HTTP client that I like, right? You remember that is just HTTP communication. So what I do, I get the IP address of my cluster and say coffee shop, that is the default context route by the coffee shop WAR file. Then resources, that is typically the JAX-RS path, the application path that I choose for this. And then I could go to my orders resource, or first of all, I can use a health check resource to say, oh great, it is up and running, 200 okay, and it tells okay, great. Seems to work. So now let's ask for the coffee orders that are there. Get to this orders resource that tells us, oh nice, empty JSON array. Okay, no coffee order there, we didn't order one, right? Let's order some coffee now. How do we do this? We posting this JSON for the coffee order to this resource. Let's briefly have a look how that looks. Order coffee with this POJO. That POJO is, it's a nice story about the bean validation integration. We can automatically validate that and include this with HTTP headers. It will return 400 bad requests. If not, that's a nice JAX-RS feature. But anyway, it will also be deserialized from JSON by JSON-B. That's included in Java 8. And that, well, has some information that we most of all can ignore, except the type, which is the coffee type. So you can have a latte like this one, or you can order an espresso or something else. And this is what we're going to provide. So let's do this. Let's say we're going to post some JSON here. Just have content type application JSON and the type that is, let's say, espresso. Yeah. And we're going to post this to our system. And then luckily we have, oh yeah, good news, 201 created. Great. We now created an order in the system. And we can even query it and say, great. Espresso is there, has just been created. So that's good news, right? Now it works. You don't believe me? I mean, you saw the code, right? I just invoked it, and apparently it invokes the other system, right? Because that's what the source code showed. And source code doesn't lie, right? Well, this is hardly enough for production, I would say. It works for demo, that's great. But now this is the point. We use the Java EE application with a default Java 8 approach. That is deployed on Docker, on Kubernetes, which is nice. We can easily set that up in a bunch of minutes. But this is hardly enough to run it on a production system. So, for example, we want to have a little bit more observability. What happens in the system, actually? Well, we don't know. If we look at our fancy diagram, we might see, yeah, this system probably calls the other system. And apparently it worked, so we can assume that the barista system has been called with the correct information, right? But we don't actually know what's going on there. The same is true for other concerns, such as resiliency. What happens if the barista system goes down? I don't know. There will be some error, I guess. So this is now where our service mesh technology comes into play. And I want to show Istio to you. Istio is the, I don't want to say de facto, but the probably most widely used service mesh technology right now that runs on so-called Envoy. Envoy is C++ technology proxy and supports Kubernetes out of the box. So actually what I just have here, my cluster, what I didn't tell you, it's not only a Kubernetes cluster, which is what you saw, it is also an Istio-enabled cluster that I installed here. So out of the box, it comes with a few features that are already helpful, that provide more observability without, and that's the point, without requiring our application to change. So what I deployed here was, you saw it in the POM XML, was simply a Java EE application with Java E8 provided. That's it. That's the only API I used. But now I, even though, can have a little bit more observability. Let's have a look at this one. What is this? That is Grafana. Grafana is a monitoring solution that includes, well, some technical monitoring here for my application, and I did not set that up. That comes out of the box with Istio. But although I did not set it up, it already includes, coffee shop and barista service. Because it will talk to Kubernetes and do an auto discovery of all the services that we have, and we can already see, well, there's something going on here. So in order to properly see something, I just ordered a coffee, right? Ordered another one. Oops. Let's pray for the Wi-Fi. Otherwise, it will be boring. Otherwise, we just ordered one. So what I want to do, I want to order a little bit more coffee so that we actually see that this works. Do I have? Yes. Oh, there we go. More coffee, more coffee, more coffee. More coffee. Let's create a little bit more, right? We are very sleepy after lunch. We need a lot of coffee for this room, otherwise we're falling asleep. And once we created all that coffee, we hopefully can see in our monitoring solution that now there are more requests going on here. I hope that it didn't kick me out of my port forwarding. So what happens is that you can use these dashboards to already see some technical information about your requests. For example, you see the success rate. Success based upon HTTP information. So HTTP status codes, you can see the request duration, and well, everything that we can include on a technical level. The same is true for the barista system. So you can, okay. Wi-Fi, bear with me. So this works, that's quite interesting. The ping works. Let's do this again. Okay, this works now. Oops, unexpected error. Probably kicked me out of my, yes, these are my port forwarding. Let's restart them. If we're lucky, then we see, so that happens if while we're in that dashboard, the connection breaks. Oh, you saw the refresh. So now we got a success rate. So that's also good news. This was the technical monitoring for both the, for both the coffee shop service and the barista service. So now we can already assume that it worked as expected because the barista service definitely is being invoked. It is included in our communication, and we can also see that the, well, not yet, if it refreshes, that we have some invocations here from the other coffee shop service. So that already provides some observability out of the box, which is quite helpful. We see what requests are going on in our system. We see the request duration and all kind of technical information, technical monitoring data that might be interesting for us. What is even more interesting in terms of specific requests and understanding how our requests go through our system, go through our mesh of microservices, is this cute little guy. That is a distributed tracing technology with the German name Jäger, and that guy can trace individual requests. So what we can do, we can go to the cluster and ask for specific traces. So what I do here, I on purpose trace every single request, include some information, and let's have a look at one specific request where we can see there is I don't want to stand in the way, there's a request coming in from the so-called ingress gateway, that is the entry point into the cluster, and then it will do a synchronous call from the coffee shop to the barista service. So this is one particular request that we can trace here that can also, for example, show us some more information about that request. So for example, this is an HTTP call. We are posting something to, well, barista 9080, so on, Bruce. So this is exactly the call that you saw in the code. Right? This is what we're doing here, and you can see that this is a synchronous call that goes into the first system, then synchronously to the second system and returns. So that is very helpful information if we want to understand through which individual instance a particular request went through. So with two systems, it's kind of trivial, right? But if you have more and more services in your mesh of microservice deployments, then this can become quite helpful to understand, well, what is actually going on in the system. Also comes out of the box with this Istio integration. Another nice story here that is also looks quite boring for now, but can become quite interesting, is a service graph that is included in Istio here. If we activate it, it's called Kyiv. Nice technology to provide a little bit more observability also. So we can draw these fancy graphs, and I will explain in a second how these Istio resources work. So it also understands how this Istio setup is configured in terms of so-called virtual services and routes that we have, and it can display a little bit more information, which for now looks quite boring because we only have one version of that application and one version of that. So we have a simple graph here. Now the question is, how does this magic work, right? Without enhancing our application, how do we get this monitoring data or this tracing information? How do we get this observability? And how it looks like when we deploy our application into a service mesh technology, because I told you the cluster that I have is actually an Istio cluster, is as follows. We still have our coffee shop and our barista service that is still there, but now instead of having one container for each and every pod, we have two containers. Still our main container, that is our running application, and a so-called proxy container, so-called sidecar container. These are now these envoy proxies that are co-located with our main application and that act, well, as a proxy. So for each and every pod, if we had more here, then each of them would have two containers. For each of them, we include this proxy container. And then what actually happens is, if we make a call to our coffee shop application, it in fact ends up at the proxy container first, and then this will, or it might, forward to our main application, to our main container here. And the same is true for our main container. If that one wants to access another application, then it also goes through the proxy, goes to the other proxy, which then calls this main container. And the same is true for the returning connection. So now you can already see, or already guess, I guess, that now the proxy can enhance all kind of information to our communication. So for example, the proxy can scrape all that monitoring data or log externally, store that away where we can access this information. Or the proxy can even intercept your communication and say, for this and this, we just kill the communication, we just don't let it through, or a few other things. Or you can reroute traffic by saying, hey, the main container just said it wants to access this system, but actually I, for some reason, want to go somewhere else. So you have the full control where the communication will ends up. And that is a very powerful way, a powerful concept to do so. So what happens, for example, for our monitoring data is that the proxy containers, they will scrape and gather that information and then just output it to the Istio service mesh. And the same is true for this Jaeger technology for distributed tracing, is that we include these open tracing HTTP headers in our communication. They are de-factor standards. These are the X-B3 span trace and so on and so forth, correlation IDs that we add in our communication in order to, well, correlate all these multiple requests. And they are then added. So one thing to mention here is all of that works out of the box with, of course, Java EE or even standalone Java. If we would use some JDK HTTP client, same story. We could also use curl there inside the container. It actually doesn't matter which technology we're using, except one thing. For the distributed tracing to work, we have to take care of one thing, that inside our application, we're going to pass these correlation IDs towards the next application. Why? Well, because otherwise Istio wouldn't, or this tracing technology, wouldn't be able to correlate these two requests. It will only see one request here and another request here that coincidentally happened at the same time. But actually you want to correlate them using these IDs. So what you have to do inside your application, if you have the incoming request in your app, in the JAX REST boundary, you have to take all this context information out of it, these headers, and then keep them in your thread. And once that thread ends up at the HTTP client, take all this information, include it again in all the HTTP headers, and pass it on. So basically that means you would have to go here, take the HTTP servlet request, take all the header information, then go here, then go here, then go here. Take that information again from the current context and include it in your request. Say request.header this, .header that. Fortunately, we don't have to do that. Why? Because if we enhance, and this is now a nice story about the current state of Java Enterprise, if we enhance Java EE or Jakarta EE with one extension that is shipped by microprofile, it's called microprofile open tracing, we can actually tell our application server, our OpenLiberty that runs there, please do that out of the box if you have that tracing information at the incoming HTTP request, which is a very nice way to, well, for us, write less code and to still be able to include that. So I don't even have to specify that in my POM XML, because in my project, I don't even want to use it. But this is an example server configuration for my OpenLiberty. So the nice story why I use OpenLiberty, beside that fact that I work for IBM, is that this application server supports not only Java EE, but also microprofile, which is an extension or slash alternative for Java EE standards that includes open tracing. And this open tracing, when activated here, will make sure that all the headers, that the header information are passed on the current thread local to the next, well, HTTP client, basically through that application, and this is why this open tracing here works. And if we would inspect the HTTP information there, including all the HTTP requests, all the HTTP headers, then we would see the correlation IDs that they match this request in the incoming and outgoing HTTP connection. So this is a quite nice story. In other regards, rather than observability, what we can also do in Istio, while we can control the overall traffic, how our individual proxies route the traffic here. Or we can include some resiliency. I told you what happens if that second application, that barista service, becomes unavailable, right? And specifically, well, quite on purpose, what I did here in my client, I used the HTTP client without specifying timeouts. So what we can do here, since JAX REST 2.1, is specifying HTTP connection and read timeouts, which is really good to do. You should do it. Why? If you do not specify, let's do this for a second, new builder, connect timeout or read timeout. What happens if you do not specify them? Well, you use the default for HTTP clients, which in some implementations is infinite, an infinite timeout. And I hope I don't have to tell you that this is a very bad idea. Why? Because what happens if your external system becomes unavailable, you basically block the thread forever, which is bad. I mean, you have a bunch of threads in your thread pool and you can create new ones, but ultimately all of the threads in the thread pool are gone and then your application is stuck and you can restart the server or kill the pod. So always include proper timeouts, like read timeouts and connect timeouts. Anyway, if you do not do this right here, or if you use some HTTP client or any technology that does not support that, well, at least we can enhance it and use this feature in Istio, in a service mesh technology. Why? Because our proxies have the full control over their connection. And if the proxy here, for example, detects, well, a timeout there, because that proxy actually can include a timeout as well, then it can at least, well, return with a proper error response and not just never respond, not just run into that timeout. That works because both of these things run locally. There's not actually a network connection going on here. This will always be the case because it's guaranteed that two containers in the same pod will run on the same node locally. So that runs on the same hardware. So what we can do, we can enhance the route definition that we have in our project. So they are done here, also in our YAML files. These YAML files, definitions, they look pretty much like Kubernetes definition. And that is actually another nice story of Istio. It integrates very well with Kubernetes. And in fact, we can extend the Kubernetes resources to use something that very much feels like a proper Kubernetes resource definition. So in plain Kubernetes, there is a service, but there is no such thing like a virtual service or like a destination rule. That comes from Istio, and that extends that definition here because we're running in an Istio cluster. So we can define a so-called virtual service here and destination rules. What that is, a virtual service defines, well, routes information where we want to route that traffic that goes to this virtual service barista. So our virtual service barista matches the actual Kubernetes service here, and we have a very boring default route rule that says everything that goes here just route it to barista, to the actual service. With that subset, v1. So we can actually, that's a best practice, we can define so-called subsets that for here is also the default, that takes a version, but we only have one version, for the so-called destination rule. Destination rule defines further policies on, well, our destinations, the subset for the barista, for example, where we could add some more, well, features, for example, resiliency related. The same is true for the coffee shop. For the coffee shop, we have one more thing that is called gateway. A gateway is very much like a Kubernetes ingress, but uses, well, a few other approaches, can do a little bit more, and it can already, for incoming traffic, routes also to these proxies, to these proxy sidecar containers. That is why we use this, well, gateway for our cluster. And what happens here, we also have a virtual service for the coffee shop that uses this incoming gateway and routes everything, well, same story, to coffee shop version v1. So that is very default setup. That is actually also what we can inspect in this Kyiv response, because we have the version v1 here that says, yeah, this is the version that goes into the coffee shop, and we actually see what we can have some, where's my mouse? We can have some nice animations there. We can see where all the traffic is going through. Well, everything is routed to v1, so that's kind of boring. But if we had more resources, then we could actually see a little bit more. So let's do this. Let's just for fun create a new version to see that we have another version 2. So I just told you, barista. Never write that code that does not include a timeout on the HTTP client. So let's do this. We use now JAX-REST 2.1, the latest version that includes a read timeout and a connection timeout. And just for the sake of the example, I use seconds for both build. So we now use the proper new builder that sets the timeouts in a standard way. Well, and let's deploy this. What do I have to do? This is the coffee shop application. So let's go to coffee shop and let's rebuild our application. We do the Maven clean package, and then we do a Docker builds, coffee shop builds version, not push, build version 2. Nice story about that is we just rebuilt the WAR file, but I told you with this thin deployment approach, this is super fast because the WAR file does not contain much. But I can already, well, see that. Let's see whether the push works, but luckily I prepared that up front, so there is already a similar image there. Well, that's quite sad. So the Wi-Fi is not very nice to us. But what we can do then, assuming we have a new image with a version 2 there on our Docker repository, we can now deploy that version also. If we say, and now we have multiple ways available, we could simply, that's the default Kubernetes zero downtime deployment approach, update that image here from 1 to 2, say kube control apply, and then we have a new version, right? And Kubernetes does all this gradual rolling update deployment approach, right? You've probably seen that. That would be one way. But now if we say, well, we actually just for the fun of it want to use these Istio traffic routing features to say we want to have both applications there at the same time, V1, V2, an old version, a new version, and then just, well, maybe gradually route them, like in a canary release approach, where we just route a tiny percentage of the traffic to the new version, or just switch it completely, but check it manually and then switch it back if it doesn't work, if we're not sure, or include that, of course, in a proper testing approach with an automated approach where we would do that, switch the traffic, run our end-to-end test, or switch it back if it fails, and so on and so forth. So instead of updating the version from 1 to 2 here, what I do instead is I actually want to have an own new deployment, just for fun, that I call, that is a bad name to do this manually. So usually that should be done in an automated fashion if you do so. But on purpose, I want to create a second deployment that also has one replica, but uses a different version label. So then my Istio traffic can be routed to that as well. Uses the new image, of course, and that's it. Same story otherwise. And I can include that. And now in the routing, what I can say is I have this routing definition that routes everything to subset v1. Okay, that's fine. But the same should be true for, well, also include v2. And then if I have two destinations, well, I can specify actually a weight to say, please do 50-50, oops. 50% to version 1, 50% to version 2, and route this to the specific destination. And of course, I have to include this in the subset as well. I include a new name of a destination, basically a new destination here that routes everything to the second version. And if I update that, then what happens is I will have a new deployment, the coffee shop v2 deployment, and I will have new routing information that includes this new destination, and that will hopefully be shown in my service graph that I had here. Oh, Jesus. Let's see if the Wi-Fi is nice to us. Because our traffic, the code change that I made here, is not usually visible or not immediately. So I just want to include that to route some traffic there up front to see that up front first, and then see whether we have an update in the service graph. So hopefully that works. Do I still have network here? Control apply this, please. Well, yeah. that doesn't work, I still have a backup by using my phone for tethering, if that Wi-Fi is nicer. So let's quickly set that up, because then you hopefully will see that example up and running. Yes. Oh, very good. Do I have an... Now it should work. Yep. Well, not much faster, right? Oh, there we go. Let's place this here. Then what happens is that we can actually... Now let's restart our coffee shop example. Server is unavailable. Okay. So what happens now, I assume, that's quite interesting. The server is unavailable, that it was reconfiguring at first. That's another thing you want to be aware of, to take the reconfiguration time into account. So gradually reconfigure the Istio and Envoy proxies. So you will see that. The other one is if we include, so I'm assuming we have a timeout there from my first application, because it now includes the timeout on the code level. And then I hope, well, I probably have to restart this one. These are my kube port forward in the Kubernetes. So let's reload this console. Yes, using all the default information here. And now you can see, well, a little bit more interesting of a graph is that we now actually have two versions, V1 and V2 here, that comes from that workload, that comes from that deployment. And we can also see, well, it's not quite green. Now it gradually becomes green as the application is available. So it will also, this Kyiv technology, it will also show us if we have some errors here, some erroneous responses. The same is true for our, let's go to the first application, for our monitoring, of course. So if we had some, let's reload it. If we have some requests that are not successful, it will show us, of course, the monitoring. That's why it's there here in our specific monitoring information. So by doing so, we just, well, increase the observability in our technology, which is a nice story. Well, again, Wi-Fi is not really nice to me. Now it's a slow tethering via phone, so it's not going to get better. So this is how we can increase the observability and have some traffic routing examples. What is also possible, rather than only rerouting the traffic, I told you we can include some resiliency features. So for example, what we can do, let's make this, let's keep the subset here, but let's say we roll back this approach and only route to the first version that does not include our timeout that we have here. But what we can do instead is to say we want to include a timeout here. So what we can specify in our route definitions in Istio is, well, resiliency features such as a basic timeout. Or on the destination rule, we can also have something like a circuit breaker / bulkhead pattern. That is all described in the docs. Actually, this is a nice example why I dislike the YAML format. Because if you edit it, you never quite know whether this is correct, or this is correct, or this is correct. No, this is correct. If not, then hopefully the Istio control will tell us otherwise. So what we can do, I always use kubectl apply to update these definitions that are placed there. So we can use this, or we can also use the Istio control, that is another command line that does some more validation out of the box, and it will tell us if something is wrong there. So for example, we can update the routing information here. That's a nice story about this Istio integration in Kubernetes. You can use the kubectl command line tool to, well, use all the Istio resources as if they were shipped with Kubernetes. So, for example, we can ask Kubernetes for all the virtual services that are there, which is quite interesting because this would not work out of the box with the stock Kubernetes cluster. Kubernetes does not know about virtual services, but if we use this extension, then it does. And it's the same look and feel and developer experience as if we use, well, a default behavior. Same is true for gateways and for destination rules and all that stuff, which is quite nice. So what we can do is this, did this work now? Yes. So I include the timeout here by including the timeout into the first rule, into the first virtual service. Did this? Oh yeah. There's an error again. Let's recreate that forward. And now if we do a reload here, then hopefully we should be able to see, yeah, this is now not being used, and we see the traffic that only goes to the first version again, if that has been updated. Yeah, so that takes the last minute, so that slowly will show less and less by the last statistics. And then, well, we now included a timeout to the first rule, to basically this graph. So if our application would not support the connection timeouts out of the box, well, we can do this using our Istio resiliency features. So now it's safe, right? Now we have the timeout. Yes, no? You don't believe me? Well, how do we test it? Because we have a successful response. Because obviously, the response is faster than 1 second. Our second system, the Barista system, does not take more than 1 second to respond. Well, in order to test that, we actually have another feature in Istio available for testing purposes, where we can say, if we have all these proxies, what if that proxy, on purpose, does something wrong? Just to test the connection and just to test the resiliency of the other application. So for example, we could say, oh, just for fun, wait a little bit and respond slower than you would typically do. Or, just for fun, include some error response. Throw away the original response and just say, oh, 500, I'm sorry. Just because we can, just because for testing purposes, that might be good in order to see whether our first application reacts appropriately. So what we can do in our Barista routing is to say, oh, please include some fault. For example, include some delay. What we can do, we can add some fixed delays, such as 3 seconds, but not all the time, but only in 50% of the cases. Just for fun. Please don't add that in production, but, you know. Or maybe your application is too fast, then you can say, oh, just slow it down a bit. So what we can do, we replace the deployment routing here of that, and then what happens is, now we tell Istio actually to, well, respond slower. And then, well, in some cases, we will actually have the timeout, or you can see it here, created, which will be roughly 50% of the cases, because we included the timeout in the first route. So if even the Barista service takes now 3 seconds, this call will actually take not 3 seconds, but 1 second, because after 1 second, the first timeout will just say, oh, that's too long, kill the connection, return a proper error, which is here a gateway timeout, 504, and then just return faster. And we can also see that, of course, in our monitoring approach, with the technical monitoring that will now show us that for the coffee shop, the request duration just went up to, well, max 3 seconds. And also in Jaeger, if we go back and search for some, is it still running? Yes. Search for some traces here to include, well, same story. If we then would find a specific trace that includes that error, then we would see that there is an error after, well, exactly 1 second, and it will return an error response and not wait for the response of the second service, of the Barista service. So instead of the nice span that we had before, we can now say, oh Jesus, what's failed to fetch? That's not good. So let's see. Okay, there's an error here. Let's port forward that properly again. This is due to the poor network connection. There we go. There's our cute Jaeger. So we now, let's find some traces, and these are all good. That is also good. This is not what I wanted to see. I wanted to see, let's search again. Wanted to see an error response. This is a policy, this is something else. So depending, oh, there's one. Oh no, that's a policy check. That's also an error. This should be, yes, that's the correct one. We go into the cluster, and this coffee shop would actually call the barista service, but it does not return appropriately. But after 1 second, it will say, oh, that's an error. And you will see the error response here, that it does not react appropriately but have the timeout here. So of course, with all that observability provided, you can now see what's going on even in these cases. And these are just a few examples that you can do with Istio, that you can enhance existing applications without changing actually the implementations of your application. Even if you use plain Java Enterprise that does not include monitoring or distributed tracing out of the box, well, with tracing you can add some extensions if your application server supports it, but that are provided by the environments, by the service mesh technology. So here you see another diagram how that works. Under the hood, Istio includes a so-called pilot plane that, well, scrapes all that information that comes from these proxy sidecar containers, and of course that also reconfigures all these proxies. So what you literally span up is this mesh of interconnected microservice deployments that always talk through these proxy containers and that are configured by our pilot plane. So this is how the architecture works. And by doing so, you can have, well, these interesting setups to enhance your existing applications. So as key takeaways for service meshes in general and how they're implemented with Istios is service meshes are a technology that transparently add some cross-cutting concerns that you might need for production deployments to your microservice deployments. Concerns such as, well, what we saw, observability, resiliency, right? Or traffic management, or even security such as authentication or authorization. All these things without changing our application. So in a sense, what happens is that we have kind of AOP, aspect-oriented programming, but for applications, right? So it's the same idea, it's the same programming model that you would have if you use Spring or Java EE, right? What we do when we're typically programming, well, we write a Java class or a Kotlin class or something else, and just by annotating it with something like @bean or @path or @stateful, then just by doing so, it becomes a HTTP REST controller and will handle all the HTTP headers for you, or it will handle all the database transactions. So that is aspect-oriented programming, and you have the same idea here, but for whole applications. So if we want to add these concerns to an application, we do that from the outside of the application in a declarative way using this Istio approach. And what I believe is a very good fit for that is using our Java Enterprise that we typically use, or that a lot of enterprises use to implement enterprise applications in combination with this new cloud-native technologies, because that fits the approach actually very well. Because if you use plain Java EE, such as I did, Java EE 8, it out of the box does not include monitoring or a lot of resiliency features. But you could actually ask the question whether you want to include that on all the applications. Because what happens if you have many microservice deployments, then by shipping all of that in the application, you would, well, ship this to each and every running application, right? To each and every instance, always including monitoring, always including resiliency and circuit breakers and whatnot, if you want to have that on the application level. But by using this approach, you actually say, well, my application should not be concerned with that. I don't want to ship that in my implementation. I actually want to ship my business logic in my application only in the Java code. And the rest is basically provided from the outside. And that fits the approach of Java EE actually very well, because what we always had in the past is that you write your business logic in plain Java and use just the APIs, the interfaces and annotations from Java Enterprise by annotating your code. And all the rest is provided by, well, the underlying layer, which is the application server or application container. And now you take that approach further and say, well, we have some more concerns here that we want to add, and they are added from the outside, from the underlying environment, from the Kubernetes cluster or from an Istio service mesh, for example. So then what happens actually is that on the Java code side, we enterprise developers, we can focus on more on what should actually focus on, that is implementing business logic. Spasibo, and thank you very much for your attention. We have a question. If we have time. Otherwise, I'll be available and running around if, depends, we probably need room. Can we take some questions or? Thank you.
This is the way we're gonna write the applications 5 years or few years from now. So, but a question to you. So I have a few apps on Kubernetes cluster.
Mm-hmm.
So they're already like working and executing some bots, I know.
Right.
So can I integrate Istio incrementally? So like an app would consist of a namespace in Kubernetes, then it would have some resources,
Mm-hmm.
deployments, ingresses, services. It's already running, right?
Yes.
So can I integrate Istio incrementally into the application?
Incrementally, generally yes. So in terms of features, yes, because out of the box it would not do anything, it would not interfere with your application if you just use the default routes. In terms of how you do the transition is, you have one, well, small breaking change where you have the first time when you would deploy this gateway, how you actually run in production, right, with probably some SSL certificates and whatnot.
Yeah.
So what you typically would do is set up as a separate Kubernetes cluster or a separate namespace at least, and then have this running applications, including all the configuration, all the SSL certificates, and then just switch by a DNS rebalancing, for example, to your new approach. But then in terms of features, well, yes, you can. You simply enhance your Kubernetes cluster with these Istio resources, and it doesn't interfere with what you have right now.
Okay, thank you a lot.
Yep. 2 more questions?
Hi, thanks for the talk.
Thank you.
Just a few questions. First, is there like data on how much latency and CPU overhead is added by the proxies?
Mm-hmm.
And the second, I guess, is there a solution for if we use managed cloud databases? Can we still trace the calls that go to these databases?
Yeah.
And that's probably it for now.
Okay. First, your first question, I always get that question, like how much overhead is added. But well, in terms of CPU and resource consumption, that's easy to calculate. It's basically the sum of all the resource and all the resource consumption of all running proxy containers, right? So you add quite a bit of an overhead in terms of memory consumption. Well, because you have, for each and every pod, you have now one more running container in your whole cluster, right? And then with the default monitoring solutions for Kubernetes, you can actually see how much memory your proxy containers consume. So that's basically that overhead. In terms of latency, it's, I would say from experience, neglectable. Why? Because what you have, it's the same latency that you would add for a reverse proxy, right? Plus, the connection between a main container and the proxy container, that's done locally. So you don't actually have a network call between the two of them. And besides that, well, Envoy is written in C++, so native language, and you can then measure how much latency that would add.
But you can't like name any like article or something from the top of the head to take a look into.
There is something in the Istio documentation. They have some performance tests how much that adds. To your second question, with the database or any other protocol, it depends. So first of all, you can always just use TCP connection or anything that you do today that just works. In terms of observability, well, it depends on the protocol. So for plain TCP and actually also for HTTPS, for SSL, inside the cluster, you would not have that observability on an HTTP request level. I mean, that's obvious because you cannot look into it. It's either TCP or it's encrypted, so you don't see it, right, from your proxy containers. What you can do is
GRCP and like other classical inter-process communications like gRPC.
Yeah, you would not see that out of the box unless there is something that your Envoy proxy supports, right? So that's the case for HTTP, or you could write an extension. So for now, only that is supported.
Thank you.
Yeah. Thanks.
Hi. My question is, 2 years ago, when I started to write my site, everybody talked about Aurica, Zool, and Hystrix. And of course, I implemented them in my code, even before there was JHipster. And then came JHipster, which basically did everything in 20 minutes.
Right.
And it still does. Istio is a service mesh that does what Aurica, Zool, I'm guessing it contains everything inside it, but currently, like you said, the business logic is not separated completely from the Zool, because let's say you use JWT stateless authentication, a lot of people, a lot of companies save data on the customer inside their JWT. So how can you integrate, so this is a more difficult situation in order to integrate Istio inside your code, because I'm already using everything I did with Zool and Hystrix.
Right.
So what is the best approach if I want to upgrade to Istio? Or is it like write everything new and that's it?
Yeah, I got your question. What is the best approach for the transition? So first of all, it doesn't matter that much that if your application supports all of that. The same is true for Spring in general. You could add, monitoring and all that to Spring, or Zipkin for distributed tracing. It does not interfere as long as, well, depends on your approach. So for example, if you have a timeout and both applications specify, or both things specify the timeout, then whatever happens is triggered first. Will be the first. For monitoring or anything else, it does not interfere with what Istio does. So if Spring, for example, does its own, or Eureka does its own service discovery, and you go somewhere else, if you define a service for it, then it works. But what you can do in order to do the transition, deactivate one or the other at first and say you just include a default route either inside your application and just say you basically deactivate Eureka or always go against the same target, and then, for example, your Envoy proxy with Istio specifies where that target ends up to. So that would be a way for a transition that you do not throw it away immediately because it's there and it works. You just leave it as is and say, okay, it does not interfere with it. And then you just gradually change it by deactivating it or by just setting it to a sensible default. For example, for service discovery. Or for circuit breakers, deactivate them or say, well, they do not interfere. If one triggers first, it doesn't matter. Well, then just the application triggers first, and then it doesn't even call the external system. That's also fine, right? There's nothing bad that happens then. Of course, it's unneeded. It's somewhat dead code in a sense, but you can deploy it there first and then deactivate it in the later run.
Yeah, thanks.
Yeah, thank you. Okay, then thanks a lot for all your questions. And well, if you have further questions, you can find me outside. Thank you.